is a bit different from your standard commercial firework. It's a homemade firework. What is required is a fuel. The fuel I'm using here is icing sugar, same sort of fuel that you or I might use. You need something to burn the fuel, so you need a source of oxygen. We're not going to bother using the air. We've got a solid source of oxygen. That is chlorate, which is ClO3. Chlorine atom with 3 oxygen atoms. That means it's got loads of oxygen and it's a solid. It's actually a negatively charged species, ClO3 minus, and so that has to be partnered by a positively charged species, which in this case is potassium. And because it's potassium, oh come on, obviously not got the mix, it's a bit damp I think. We might just give up with the fireworks. I should have checked that. Now what's happened there is I think I've got too much fuel and not enough oxygen. Well, we'll try, because that will be, let's try the sodium one then, because it's got a little bit of nitrate in it as well. It's been a bit damp recently, I think that's what the problem is. Right, so let's try the sodium one. Better, but still, wow. They worked last week. I think I've learned my lesson. I'll always prepare this stuff absolutely fresh. Last week's not recent enough. Right, let's try the barium one. This is slightly less hygroscopic, so it might work. Right. What is up with these things? Well, we can at least see well, I can see that there's some green colour there. Pretty certain the strontium won't work. I shall one last vain attempt to try this. I don't think it's going to work. So, I guess no, I think the answer there is I needed drier species and I needed more oxygen in it. So, again, it shows you that I don't like to have two things in a show not working. It's a long while since that's happened, but none of us are perfect. So, that didn't quite work. I didn't get my stoichiometry just right. So we're not going to have fireworks, but never mind, this always works. This is hydrogen plus oxygen. That's a reliable reaction. It's pretty hard to not react hydrogen with oxygen. So let's fall back on something more reliable. This time I'm going to make the hydrogen. Because I'm a chemist, I know how to, I'm in control of the atoms. So I've got some hydrogen atoms here, partnered with chlorine atoms, HCl concentrated hydrochloric acid, HCl in water. And in there I've got some zinc metal. And if you're doing GCSE science, you will at some point need to learn that when you put any metal together with any acid, you get hydrogen and a metal chloride. So here we're going to make zinc chloride. And while that generates hydrogen and fills that syrup tin with hydrogen, give me a chance to put the screen up, because we don't really know where it's going to go. And once I'm sure that there's been sufficient hydrogen generated to displace all the air in that can, and that's very important, then I will light it. And if I've waited long enough for all the air to be displaced, then it will burn in a controlled way. There we go, right. So that's me set light to some hydrogen, and it hasn't gone bang. It's burning in a controlled way. You probably struggle to see that flame unless you're right at the front. It's not a very luminous flame, the hydrogen flame. It's burning in a controlled way. It will continue burning in a controlled way, just as if that was the gas burner on my gas cooker at home. And just like my gas cooker at home, it will burn in a controlled way unless there is a leak. And if some air gets into the system, like for example, if the tube fell out the bottom, it will continue burning at the top, using up the hydrogen, and that will suck in air from the bottom, and eventually you'll get an explosive mixture of hydrogen and air, and it will go bang very loudly. So, fingers on ears. That was a good one, eh? back in the groove, hydrogen plus oxygen, my favourite reaction never fails. So, one thing, that was louder than the balloons. There was a lot more hydrogen in the balloons, but one little tin of hydrogen violently banged. That is because I hammered the lid on. I was trying to keep the energy in. And whenever you try to contain a reaction, then that's when it's more likely to overcome that, and you get suddenly all the energy comes out at once, and you get a true explosion rather than just a deflagration. Now, we managed to get the syrup tin lid to go pretty high. I don't think we hit the roof this time because it's a very high roof, but you saw there was plenty of energy. When the hydrogen reacted with the oxygen, you got a lot of heat, and that expanded all the gases, and that pressure sent the lid up into the air. Therefore, we could in principle use that energy. Imagine that was a cylinder of a car engine. It can make a piston go up and down, make the wheels go round in your car. We could use hydrogen as a fuel. And there is one organisation that's used hydrogen as a fuel many times, really. It was NASA, because NASA put the space shuttle into space, and that big tank you saw in the space shuttle stuck on the end of whenever it was getting sent up into space was full of hydrogen and oxygen. They used hydrogen plus oxygen to get the thrust to get the space shuttle into space. And they did it many, many times before space shuttles finally retired just a couple of years ago now. So this here gas bottle is going to be our homage to the space shuttle program. This is a University of Manchester rocket. It used to be a lemonade bottle. We filled it full of water this morning, and then turned it upside down, and I bubbled some hydrogen in until it was about that much hydrogen. I've then just let all the rest of the water out, so I've got that much hydrogen and I've got that much air. And there's about that much oxygen in that much air, 20%. That much oxygen should be just about right to burn that much hydrogen. And if I've got my stoichiometry just right, then we should be able to make that